Welcome to this domains video on kinetic theory. In this first video, we are going to have a quick overview of kinetic theory, and we will go through some of the key definitions that will be really helpful in helping us to understand and teach concepts around energy post-16. An understanding of kinetic theory and the associated gas laws is vital to help us explain many of the natural phenomena and objects around us. From the creation of perfectly aerated foods like marshmallows or cheese puffs to jet engines and the ventilators that save so many lives, kinetic theory underpins so much of what has advanced us as humans. If you have taught younger students, you may have shown them this model of solids, liquids and gases, little particles drawn as ball bearings in a box. On heating, these particles have increasing energy which is stored kinetically, and which gives solids, liquids and gases many of their characteristic physical properties. We will stick with this model, but we will refine it so as to enable us to do calculations which you can find in a later video. Particles in fluids, that's liquids and gases, move randomly and with different speeds. They collide and bounce off each other at random. If they are in a container, they can collide with the size of the container, exerting a tiny force. Brownian motion is named after botanist Robert Brown, who first described the phenomenon in 1827 whilst looking at pollen grains immersed in water. Have a look at this simple but effective demonstration of Brownian motion and diffusion on a macro scale. Coloured sweets are placed on a white plate with a small amount of water that doesn't quite cover them. As these sweets dissolve into the water, the molecules that make up the colour move randomly from place to place by Brownian motion, causing the colour to diffuse through the water. Diffusion is defined as the movement of a substance from an area of high concentration to an area of lower concentration. The colours don't mix because each colour has the same concentration, so the molecules are more likely to spread into clear water than into coloured water. This is a nice example of diffusion brought about by Brownian motion. Let's consider temperature and its connection to the motion of particles. The temperature of an object is a measure of the degree of hotness of the object. You can use touch to get an idea of how hot something is. The hotter it is, the greater the average energy of each particle. If you put your hand in a bucket of hot water, the average energy of each particle stored kinetically in your hand will increase, and the average energy of each particle stored kinetically in the water will decrease, as energy is transferred between the two stores. If you find the Goldilocks of buckets of water and the temperature of the water is the same as your hand, around 37 degrees Celsius, then there is no net energy transfer either way. The average particle motion is the same, and your hand is in thermal equilibrium with the water. In this diagram, the Celsius and absolute temperature scale, or Kelvin scale, are shown side by side. The Celsius scale shown on the right has a steam point of 100 degrees Celsius and a nice point of 0 degrees Celsius. The absolute scale of temperature is measured in units of kelvins. It is defined in terms of absolute zero, 0 kelvins or minus 273 degrees Celsius, where there is no energy stored thermally and minimum energy within the internal store. And also the triple point of water, where ice, steam and water exist in thermodynamic equilibrium and is at 273 Kelvin or 0 degrees Celsius. A more precise and accurate way of finding the temperature of an object is to use a temperature scale or thermometer, which has defined fixed points. Liquid and glass thermometers, like the one in this photo, are based on the principle of thermal expansion of fluids. A liquid in a capillary tube expands when heated and contracts when cooled. A calibrated scale can then be used to read off the respective temperature that led to the corresponding thermal expansion. Such thermometers are called capillary thermometers, and the liquid used in these thermometers is usually mercury or alcohol. Let's now look at heating. Heating is an energy pathway and describes the transfer of energy between objects or systems. If, for example, we think about the hot air balloon, burning a fuel raises the temperature of the gas inside the balloon, and this is an example of heating where the chemical store empties and the internal store fills. The energy stored internally in an object is the total of all the energy stored potentially and kinetically. This could be changed, for example, by a change in temperature or a change in phase. You can find out more about this in other videos. Because an ideal gas has an absence of interparticle interactions, it only stores energy kinetically. Let's look at an example. Consider the hands of this gymnast. The movement of her hands on the bar will cause her hands to get warmer due to the work done by the frictional force between her hands and the bar. As her hands get warmer, the energy stored internally in her hands will increase. Here is a nice visual demonstration of the effect of heating on the energy of particles. Glow sticks glow due to a chemical reaction between different chemicals. The reaction begins when the glow sticks are cracked and the two chemicals are allowed to mix. In this demonstration, two glow sticks were started at the same time and placed in two separate glasses of water. The glass on the left contains cold water and the glass on the right contains hot water. Greater heating of the glow stick on the right clearly shows a faster rate of reaction, evidenced by increased glowing. The reaction is occurring more quickly because of the increase in the energy stored kinetically of the molecules, resulting in more frequent collisions between them. In 1738, Daniel Bernoulli was the first to understand air pressure in terms of molecules. He visualized them shooting around very rapidly in a closed container, supporting a weight as shown, by constantly bouncing off the underside of the piston. Given more room, they would rush in to fill the new space, just as a gas is observed to do. No one believed him. But kinetic theory explains the behavior and properties of gases and the gas laws. The central idea is that a gas consists of a collection of particles with energy and therefore are in motion. He went further and suggested that these particles must exert a force. They must be doing that by bouncing off the inside of the walls. Because there are so many impacts over an area, you can have a measurable pressure on the container. The kinetic theory of gases explains the macroscopic properties of gases, such as volume, pressure, and temperature. Because of this, we should revisit pressure, the force per unit area. It's measured in pascals, and understanding pressure is very important when thinking about kinetic theory and the gas laws. I really like the bed of nails demo. With so many nails, your force is distributed over a large area. You can demonstrate this using a balloon on a single nail versus a balloon on a bed of nails. Of course, the single nail pops the balloon immediately, but you can lean very hard on a balloon on a bed of nails before it bursts. Going back to Bernoulli and his model for the kinetic theory of gases, not only did he theorize that particles exert a force or pressure on the wall of a container, but also that a relationship exists between pressure, volume, and temperature. If the volume of a container is decreased, there will be a greater number of molecules hitting the inside of the container per second. A greater force will be exerted and the pressure will increase. If the temperature of the container is increased, molecules will be moving at greater speeds. More molecules will be hitting the inside of the container per second, and they will each exert a greater total force, and the pressure will increase. The relationship between pressure and volume can be clearly demonstrated at home or in the classroom. All you need is a way of creating a vacuum and one or two partially filled balloons. You can also use marshmallows, shaving foam or crisp packets. In this example, I am using a simple vacuum container and pump and two partially inflated balloons. Place the balloons in the container and seal with the lid. And use the pump to create a vacuum. You can check that a vacuum has been created by attempting to remove the lid. If it is a vacuum, it should be difficult to remove. If the container is sealed correctly, you can see the balloon start to inflate and fill the space within the container. As the pressure has decreased, the volume of the gas has increased. As you increase the pressure again to normal, you can clearly see the balloons decrease in volume once again. This demonstration shows the relationship between pressure and volume of a gas. Thank you for watching this introduction to kinetic theory. I hope you found it useful. If you have any questions, please email me at jessica.hamer@iop.org or get in touch on Twitter at Dr. Jessica Hamer. The rest of the Physics CPD series on energy is available to watch, and there are also further resources on IOP Spark available. Thank you for everything you are doing to support young people with physics. Have a great day.